Today we are starting a very important part of medical education, that is about the autonomic nervous system and the drugs acting on the autonomic nervous system, right? When we talk about the pharmacology of autonomic nervous system, we divide the drugs into two main groups: drugs acting on parasympathetic nervous system and drugs acting on, yes, sympathetic nervous system, right? Let's suppose autonomic nervous system pharmacology, right? Primarily it is divided into two groups: the drugs acting on sympathetic nervous system, and of course drugs acting on parasympathetic nervous system. Now, in early part of these lectures, we will talk about the drugs acting on sympathetic nervous system. Again, the drugs which act on sympathetic nervous system are divided into two: drugs which mimic the action of sympathetic nervous system. Drugs which mimic mean the drugs which produce action similar to activation of sympathetic nervous system. So those drugs which increase sympathetic activity in our body, or those drugs which produce such effect in our body which is similar to the sympathetic activation, those drugs are called sympathomimetic drugs. Sympathomimetic drugs. Some people also call these drugs adrenergic drugs. Adrenergic drugs, or these are also called adrenergic agonist. So this group of drugs, right, sympathomimetic drugs or adrenergic drugs or adrenergic agonist drugs, this is the group of drug, right, which basically produces pharmacological actions which are very similar to activation of sympathetic nervous system, right? The second group here is the drugs which decrease the actions of sympathetic nervous system, and the second group is called sympatholytic drugs, or they can be called anti-adrenergic drugs, or they can be called adrenergic antagonist drugs. So we can say that basically all drugs which work on the sympathetic nervous system, they are primarily divided into two groups: sympathomimetic drugs and sympatholytic drugs. Sympathomimetic drugs are increasing the activity of sympathetic nervous system, or they are producing the pharmacological actions which are like the stimulation of sympathetic nervous system, right? And sympatholytic drugs are either decreasing the activity of sympathetic nervous system, or they are producing pharmacological actions as if sympathetic nervous system activity is blocked, partially or completely. Is that right? Now, to really having a good concept of these drugs, we must understand the neurophysiology of sympathetic nervous system, as well as you must understand neurobiochemistry of sympathetic nervous system, because primarily these drugs alter the neurophysiology and neurobiochemistry of the sympathetic nervous system. So now I will talk about that how the sympathetic nervous system normally physiologically work. Once you have understood that very well, that how the sympathetic nervous system can be activated, what are the neuronal connection in sympathetic nervous system, what are the neurotransmitters synthesized, stored and released by sympathetic nervous system, how those neurotransmitters work on the adrenergic receptors, what are the different types of adrenergic receptors, how those adrenergic receptors are distributed differentially on different tissues in the body, and how those sympathetic receptors bring physiological changes in the organ system. First we'll understand that, then we'll go to the drugs. Now, to really understand that how the sympathetic nervous system works as a component of autonomic nervous system, let's go back to some of the neurophysiology. We have a very good friend of us here. Come here, please. He is Mr. Gavin. Very soon he will be Dr. Gavin, right? So this Dr. Gavin will take as our example in which, due to some sudden stress, his sympathetic nervous system is activated. And we will see that once his sympathetic nervous system is activated, what are the changes occurring in his different tissues. Is that right? Now, first of all, we will take an example that how his sympathetic nervous system can be suddenly activated, because all of you must be knowing already that sympathetic system and parasympathetic system have most of their actions which are opposing to each other. And sympathetic and parasympathetic nervous system are working automatically, right? They are not under our will control, right? They are automatically controlling some aspect of our viscera. They are controlling some of the metabolic functions. And sympathetic nervous system activation actually prepares you appropriately to fight with the stress, or fly away from the stress. Again, listen. When you are under stress, right? I don't know, this may be a physical stress, someone is about to beat you, or it may be some verbal stress or financial stress or academic stress. But anyway, if there is sudden increase in your stress level, acute increase in your stress level, sympathetic nervous system fires, right? And it prepares your body to fight or flight with the stress. If stress is small, you will fight it. If stress is too big, you will fly away. Is that right? And parasympathetic nervous system is dominantly working in your body when you are comfortable. For example, you are in your bed, in your own bed, alone, reading some novel which is not very stimulating, right? You have taken food, very comfortable, no stress. Stomach is full, story is very good, right? There is no noise, no threat. Financially you are not worried. Even your wife is not fighting with you. One of the unusual days. You really feel relaxed. That is the moment your central nervous system is activating parasympathetic nervous system, right? But if sudden stress comes, central nervous system will switch the balance. It will reduce the activity in parasympathetic and increase the activity in sympathetic nervous system, right? So let's take example of this, our friend Gavin, that what is your age?
26.
26, he can still afford more romance. So one very beautiful night, moonlight, he was feeling romantic feeling for another new lady, but she was not available. So he was alone, moving on the road and thinking, planning, men plan so many things, right? So he's planning and feeling good, he's very confident, he will do so many things sooner or later, right? And feeling great. Suddenly, a very big, very black dog appears. And dog is barking in a very hostile manner. And when he looks to the dog, he finds that size of the dog is progressively increasing. Now you understand the central nervous system will appreciate the stress, and sympathetic system will start firing, and there will be physiological changes in his body, right? And if dog is really big and black and very hostile, of course his sympathetic nervous system will be activated and he will decide to run away. Run, not towards, away. Right. But if unfortunately dog is very small and not very hostile, just irritating him, maybe he attacked the dog. You never know, human nature. He attacks the dog and dog's sympathetic nervous system is activated. Yeah, you never know. This is life. You see? So, okay, in our example, we take a dog which is really big and black and after him and his sympathetic nervous system is activated and he decides to run away, right? And we'll see what goes in his central nervous system and peripheral nervous system and neuronal sympathetic nervous system activity. You have a seat and we deal with your central nervous system. Right. Actually, how is sympathetic nervous system will be activated? The real activity will initially start in central nervous system. Let's suppose here it is central nervous system. You understand, of course, cerebral hemisphere and midbrain, pons, medulla, spinal cord and cerebellum. Now, the main center for regulating the activity of the sympathetic and parasympathetic functions is present in the hypothalamus. Now, hypothalamus is located here. You know, here is your anterior pituitary, posterior pituitary. Now, here is your hypothalamus, right? The neurons in the hypothalamus are mainly determining that autonomic nervous system should be more having parasympathetic activity or sympathetic activity, right? Now, within the hypothalamus, there is ventromedial area and you can say anterior area and there is posterior area. Now, posterolateral area. Actually, if I draw the hypothalamus here, now this anteromedial area of hypothalamus, if this area is stimulated, you will have activation in parasympathetic nervous system. But if this posterolateral area in the hypothalamus is stimulated, the neurons in this area, you will have increased sympathetic nervous system activity. Is that right? So basically, hypothalamus is the highest center in the central nervous system which is controlling the balance between the sympathetic and parasympathetic activity. Is that right? Now, of course, when big black dog is after him, then this part of hypothalamus should be activated. So the anterior part of hypothalamus should be having reduced activity and posterolateral sympathetic areas in hypothalamus should be having increased activity so that sympathetic fibers should be stimulated. But the thing is that how the hypothalamus know that there is stress? How hypothalamus knows that there is stress and how hypothalamus knows that now I should increase the sympathetic activity? Actually, in our central nervous system, there is a large area which is concerned with emotions and behavior and memory. This area I am showing in this diagram as limbic system. In the central nervous system, there are multiple areas which are together as a group called limbic system. The function of the limbic system is concerned with emotions, with your behavior, with your recent memory, and many other functions. So now, when a big black dog is coming after him, and dog is barking in a hostile fashion, so the barking sound through his ears, through his auditory pathways, will go to the auditory cortex. Auditory cortex is in the temporal area. So, barking sound activate the auditory areas in the temporal cortex and that will give special stimulation to the limbic system. Then if he turns his neck and look at the dog, through visual pathway, image of the dog is on the, what is this? Occipital cortex, visual cortex. This will also give information that visual information is very, very hostile to the limbic system. Then maybe he is having some past experiences with the dogs, unpleasant past experiences with the dog, or maybe he has seen some movies in which dogs are really very hostile, right? Or he has seen someone suffering with the dog bite. So that memories from other part of cerebral cortex will be also activated and stimulate the limbic system. So now what really happens, that limbic cortex, or we can say emotional cortex, is collecting the information about the recent events, right? And when limbic cortex appreciate that auditory information is stressful, visual information is stressful, and the new information which is coming that is related with past information which is also stressful, then those neurons will be activated. Those neurons will be activated in limbic system, which will stimulate, which will increase the activity in posterior part of hypothalamus. And same neurons at the same time will inhibit the activity on the parasympathetic nervous system. So the balance will be altered in the hypothalamic activity. So what really happens, whenever you are under stress, from cerebral cortex, information is going, of course, to the limbic system, and when limbic system undergoes stress, right, it will activate the sympathetic components and inhibit the parasympathetic component present in hypothalamus. Once sympathetic centers in hypothalamus are activated, from there the descending pathways will be there, right? Multiple neurons, right? Chain of multiple neurons, we call it polyneuronal descending pathways. The descending pathways which are made of multiple neurons. So these polyneuronal descending pathways will be activated, and these pathways will come into lower part of central nervous system, and they will activate sympathetic outflow. They will activate, yes please, sympathetic outflow. So what really happened, when he went under stress, his cerebral cortex activated the sympathetic centers in hypothalamus, which activated the polyneuronal descending sympathetic pathway, which will control the sympathetic outflow. Now sympathetic outflow comes out of central nervous system from spinal cord. And which part of the spinal cord? From thoracic part of the spinal cord and from the lumbar part of spinal cord. So we can divide the spinal cord into, okay, this is cervical spinal cord, this is suppose thoracic spinal cord, and this is lumbar, and this is sacral. Cervical, thoracic, lumbar, sacral. So what really happens, that from here the neurons will bring the information out, right? Now these neurons which are bringing the information out, they are present from T1 up to lumbar L2 or 3, right? And these neurons, on bringing the information out, I will just show one pathway large, and they end up into some sort of sympathetic ganglion. This is sympathetic ganglion. So this neuron which is present in the spinal cord, you know where exactly it is present in spinal cord? Let me draw the section of spinal cord. In the spinal cord, these outgoing neurons have their cell bodies in this area and in this area. This is anterior horn, this is posterior horn, and this is called intermediate horn or lateral horn. So neurons which are coming from the top, they will stimulate the neurons in the lateral horn or intermediate horn. From here, sympathetic outflow will go out and go to the ganglion. Is that right? From the ganglion, postganglionic neurons will be going to the tissues. Now, let's come back and talk about that there is a lot of sympathetic outflow coming from all these areas, right? Now, one thing you should appreciate, that sympathetic outflow is diffuse. Diffuse means that multiple areas will be activated, because thoracolumbar, all the outflow is activated simultaneously. It is not possible that central nervous system activate only fibers going from thoracic segment 6 and not stimulate fiber from 4 and 5. So it's a diffuse outflow. Is that right? Now, how this outflow really work? I will take two examples only. Number one, suppose from this neuron, fibers are going out, and these fibers go to, yes, this is a nerve ending, right? This is the cell body of the neuron, axon of the neuron, and nerve terminal. This terminal is present in a sympathetic ganglion, right? From the sympathetic ganglion, what really happens, that postganglionic fibers will go and they will eventually terminate on the, yes, on the tissue. They will terminate on the tissue. Let's suppose this is heart. So then these fibers, postganglionic fibers, will release neurotransmitter on the target tissue, and target tissue will have receptors here. To make a very good concept, we have to understand that once sympathetic descending pathways are activated and preganglionic neurons fire, right? Most of the preganglionic neurons are ending up into sympathetic ganglion, and sympathetic ganglion, right, are stimulated, and postganglionic fibers will eventually end up into target tissue, right? And at the target tissue, the main neurotransmitter which is released here is, yes, norepinephrine. But so postganglionic fibers release norepinephrine at neuroeffector tissue or at the neuroeffector site. But remember, these sympathetic preganglionic fibers, they release a different neurotransmitter. Which neurotransmitter is released from here? Yes, sympathetic preganglionic fibers release acetylcholine. So you have to remember that norepinephrine is released by the postganglionic nerve ending. Preganglionic nerve endings are releasing acetylcholine. A very important thing. All the neurons which come out of central nervous system are cholinergic. No need to memorize, a basic principle. Almost all the neurons which come out of central nervous system are cholinergic. You must be knowing that there are sympathetic preganglionic coming out, cholinergic. Parasympathetic preganglionic coming out, cholinergic. Even motor neurons going to the skeletal muscle and neuromuscular junctions, they are also cholinergic. So all the neurons which come out of central nervous system are cholinergic. So of course, preganglionic sympathetic fibers are also cholinergic. And here they act on cholinergic receptors, right? And these are nicotinic cholinergic receptor. Cholinergic receptors are two types, nicotinic type and muscarinic type. Nicotinic type. Then action potential is produced over here, and when this action potential arrives at neuromuscular or at the neuroeffector junction, this nerve terminal releases norepinephrine. In this way, sympathetic nervous system releases norepinephrine on the target tissue through their innervation, through the nerve supply. But sympathetic nervous system has one more way to work. That some of the preganglionic fibers, they don't go to the ganglion, they go to the adrenal medulla. The sympathetic ganglion are ending up, these fibers, some of the, what are these fibers? Preganglionic sympathetic fibers, they end up on adrenal medulla, right? Suppose this is adrenal medulla and here it is adrenal gland cortex. And these fibers release here again acetylcholine, which act on the, what is this? Adrenal medulla cells and stimulate the adrenal medulla cells. And adrenal medulla cell release, adrenal medulla cells release epinephrine mainly, not norepinephrine, about 80 to 90%. It releases epinephrine in general circulation. Remember, sympathetic nerve endings are mainly releasing norepinephrine. Nerve ending, NE. Nerve ending releases norepinephrine, NE. But adrenal medulla releases epinephrine. Now, of course, actually what is adrenal medulla? They say during the evolution, many ganglion cells come together and lose their axons and they start releasing their neurotransmitter into blood, and that is how adrenal medulla is made phylogenetically. Now, adrenal medulla releases epinephrine in the general circulation, of course on sympathetic nervous system stimulation, but this epinephrine will circulate in the blood and go to stimulate adrenergic receptor wherever they are present in the body. It means that let's suppose there are adrenergic receptors present over here. Now these adrenergic receptors can be stimulated by the norepinephrine coming from the sympathetic nerve ending, or these adrenergic receptors can be stimulated by epinephrine which is present in general circulation. So what we learned up to now? We learned up to now that sympathetic nervous system releases norepinephrine through the nerve endings, and it releases epinephrine from adrenal medulla into general circulation. So receptors at neuroeffector sites release norepinephrine through innervation, or they receive epinephrine through the general circulation. Am I clear to everyone? There is no problem up to this. Now we have to come one more thing, that how this nerve ending work, how this neuroeffector site work, right? How this area is functioning. But before we discuss that, I will talk about the receptors, right? That how these receptors are present in the body. Once epinephrine or norepinephrine come to the adrenergic receptors, how adrenergic receptors are stimulated and what changes come into body, right? After discussing that, we will come back to this specialized area. This is a very, very specialized area because there are about 30 drugs which work only on this nerve ending and its neuroeffector site. Okay, I'll leave it up to you. Mr. Gavin, dog is after you. So you must tell me that we should discuss this area first, how this small area work. I will make a big diagram, explain it thoroughly, right? Because there are so many drugs which work in this area. Should I explain this first, or I should explain this later and just tell when epinephrine and norepinephrine is going into your blood, how changes are occurring in your body so that you can fly away from the dog?
Tell us about the drugs.
First you want to know this thing?
Yes.
Okay, he want to know first this thing, what's going on here, right? But meanwhile dog may catch you. Okay, now let's come here. Let's suppose this is preganglionic nerve endings, right? Here is the cell body of postganglionic neuron. Is that right? And this is postganglionic neuron axon going on. Now, of course, this axon must end up into tissue. What I'm going to do, I'm going to make the nerve ending out of proportion very large. You understanding? This is one of the nerve ending of sympathetic neuron, and here is suppose target tissue, target cells. These are target cells on which neurotransmitter will work, right? So let's start discussing this area, which is pharmacologically extremely important. That what's going on in the nerve ending, what is going on in the synapse, what's going on in this area, and how drugs alter the activity here, right? First we will understand how the neurotransmitter is synthesized, stored and released. Of course, all of you know the main neurotransmitter at this point is norepinephrine. My question goes to someone very intelligent, that norepinephrine which is present here in the synaptic vesicle, that norepinephrine is synthesized. My question is, that norepinephrine is synthesized in the cell body of the neuron and then transported here, or that norepinephrine is synthesized locally in the sympathetic nerve ending? Question goes to this gentleman.
Locally.
You think norepinephrine is stored here and synthesized here? It is not synthesized in the cell body.
I don't think it's in the cell.
Okay, you think it is here. Anyone who differs, what do you think, man? Here. That's right. Actually, this is a basic principle. Most of the small molecular weight, small molecular weight neurotransmitters are synthesized within the nerve ending. Is that right? So norepinephrine is a small molecular weight neurotransmitter. So we'll see how it is synthesized here. Let's suppose start with very basic. From the GIT, of course, you take a lot of amino acids, right? Proteins. You eat. Amino acids are coming here. From the GIT, amino acids are absorbed into, yes please, general circulation, and then these amino acids are distributed to all tissues in the body. Am I right? One of the amino acids which is absorbed from the GIT, that is tyrosine. Tyrosine is one of the amino acids. Now, what really happens that sympathetic nerve endings are specialized in concentrating tyrosine. There are special pumps here. There are special tyrosine uptake mechanisms here in this nerve ending. And what these are doing, these pumps, that they take extracellular tyrosine molecule, right, and pump it in. So in this way, all sympathetic nerve endings are very rich in tyrosine. Once they have taken the tyrosine, then an enzyme will work on it. I always think tyrosine is like tire. You know, tire in the car, circular. So tyrosine is also circular. What I mean by circular, let me draw the molecular structure of tyrosine. It's not difficult. Again, it's circular. Remember, in pharmacology, you are not supposed to memorize and remember the molecular structures of the drug except sympathetic nervous system, because in the drugs of sympathetic nervous system there is a very big correlation between the molecular structure and function of the drug. When you little change the molecular structure, function of the drug changes. Due to that reason, only in sympathetic nervous system, especially adrenergic drugs, you must know some idea about their structure because their function depend on that. But remaining pharmacology, you are not supposed to remember molecular structures. Now, tyrosine structure. Tyrosine is like a tire. It's a benzene ring. One hydroxylation here, right? What is this? CH2, CH2, right? What is there? The ethyl group here, and then with that there is amino group here, and there is carboxylation. Now, this is basically tyrosine fundamental structure. So what really happens, tyrosine is pumped into nerve ending, right? In the nerve ending, there is the enzyme, the first enzyme which will work on the tyrosine. What is the name of this enzyme? Who is going to tell me the name of this enzyme? Tyrosine hydroxylase. That is called, yes, tyrosine hydroxylase. So tyrosine hydroxylase work on this molecule. Listen, keep this basic molecule in your mind. This is the mother compound, or I don't know, father compound of the sympathetic neurotransmitters and drug. All the basic compounds, most of them are derived from this structure. Now, first you do hydroxylation of the tyrosine. So when you do the hydroxylation, what really happens, here a hydroxyl group is added. What is added over here? Hydroxylation is done and hydroxyl group is added over there. There is one question. You know, epinephrine, norepinephrine and dopamine and isoprenaline or isoproterenol, all of these drugs are called catecholamine also. Have you heard of it? Epinephrine, norepinephrine, dopamine, isoproterenol, all of them are also called catecholamines. Why we call them catecholamine? Question goes to that lady. Okay, she wants to know the answer. She doesn't want to know the question. Anyone can answer, because these, again and again when you read the books, you know, my duty is to make books easy for you. You enjoy the books. So many books they mention epinephrine or norepinephrine or dopamine or isoproterenol. They are catecholamines. So who is going to impress me by telling why they are called catecholamines? Yeah, you want to impress me. No. I want to know why they are called catecholamines. Of course, they have catechol ring. What is catechol ring? I've given you idea. Please impress me. Catechol ring. What is catechol ring? Listen. Any benzene ring with 3 and 4 hydroxylation is called catechol ring. That's it. Yeah, now you are impressing me after the time. You say, of course, catechol has a mine group also. So basically, catecholamines are the compound which have amino group and catechol ring. What is catechol ring? Catechol ring is, yes, dihydroxybenzene ring, where one hydroxyl is at 3 position and 4 position. Am I right? Later on we will see in the lectures of drugs that how you change the hydroxylations and drugs actions change, right? So that is why, because epinephrine, norepinephrine, dopamine and isoproterenol, all of them have this ring structure. So they are called catechol compounds, and in the end they have amino group, so catecholamines. Is that right? But whenever we remove these these hydroxylations, we say drugs are non-catecholamines. In pharmacology, we say sympathomimetic drugs are catecholamines and non-catecholamines. So you have to remember, whenever we say drug is non-catecholamine, I think its ears are removed. These hydroxylations are removed. Anyway, so tyrosine gets hydroxylated here. And once it is hydroxylated, the new compound is called DOPA. Now this compound which is hydroxylated, this is called DOPA. This hydroxylated compound, right? And once DOPA is produced, right, then what really happens in the next step is, yes, now next enzyme will come into action and convert the DOPA into, yes please, dopamine. Now, how the DOPA can be converted into dopamine? It's very easy. Bring the, what is this, carbon dioxide out. So when this molecule will puff out carbon dioxide, it will become dopamine. So the next enzyme which should be working here should be DOPA decarboxylase, working on the DOPA, yes, and removing what? Carboxyl group. So DOPA decarboxylase. So this DOPA decarboxylase, right, it work on the DOPA, and what comes out? Remove the carboxyl group or carbon dioxide. So look here, we have lost this carboxyl group, right? We can make it like this, it is lost. Carbon dioxide, like a balloon of a baby, it is going away. And who has done this function? DOPA decarboxylase. And now what is the structure present over there? Dopamine, right? So you take tyrosine and hydroxylase, you get DOPA. You take the enzyme DOPA decarboxylase, do the decarboxylation of DOPA, and you end up with, yes, what is this? Dopamine. Right? Now, as soon as dopamine is produced, there's a trouble. If it remains here in the cytosol, it will be immediately destroyed. You know why it will be destroyed? Who knows? Because it will be immediately destroyed, and prevent the destruction of this molecule, we should pump this molecule into a membrane-bound vesicle. There is a membrane-bound vesicle over here, right? And there are special vesicular transport system. And this vesicular transport system should take the dopamine and pump into vesicle. Now question is that once dopamine is synthesized, it is immediately pumped into what? Neuronal vesicles. Why? Because it will be destroyed outside. Who will destroy it? There is a cat there. Cat. Let me tell you. There are mitochondria here. You know mitochondria? What is the relationship of mitochondria here with this discussion? On the surface of mitochondria, there is a very, very dangerous enzyme, right? It is just like a cat, I feel. This is expressed on the surface of mitochondria, and this enzyme is called monoamine oxidase. This enzyme can do oxidation of monoamines. Now, what is monoamine? Yes, Gavin, don't forget about the dog. Yes.
They're dopamine.
Yeah. What is monoamines? Yes, Ronald. Compounds which are neurotransmitters which are derivative of single amino acid. They are monoamines, right? From single amino acid. Now what are monoamines? Dopamine is monoamine. It is derived from tyrosine. Norepinephrine is monoamine because norepinephrine is derivative of dopamine. Epinephrine is monoamine because epinephrine is derivative of norepinephrine. Tyrosine make many monoamines. One monoamine from tyrosine is dopamine. Other monoamine from the tyrosine is, yes, norepinephrine. Another monoamine from tyrosine is epinephrine. Is that right? Then from another amino acid, tryptophan, we can make 5-hydroxytryptamine, serotonin. So tryptophan is amino acid from where we can derive serotonin. So serotonin is also monoamine. Is that right? Am I clear? Even neurotransmitter histidine is monoamine, the derivative of histamine. And what about acetylcholine? Yes. It is not monoamine, it's not derived from any amino acid. Right? So, you know what are monoamines. So, in many of the nerve endings in central nervous system or peripheral nervous system, there is monoamine oxidase on the mitochondrion. And these monoamine oxidases can do catabolism of epinephrine, norepinephrine, serotonin, dopamine. So, you must know they are involved in multiple metabolic destructions of multiple neurotransmitters. Anyway, let's come back. Actually, if dopamine remains here, attention please, dopamine, epinephrine, norepinephrine, all of them can be destroyed by MAO. MAO means monoamine oxidase. So, as soon as dopamine is synthesized, it is captured into vesicles so that it is not destroyed by monoamine oxidase. Am I clear? So, dopamine is taken in. Now, listen carefully. If this neuron is dopaminergic, if it was dopaminergic, there will be no further reaction. Dopamine will be stored and released. But our neuron is not dopaminergic. It is noradrenergic. This neuron is noradrenergic neuron. So it means still one more work need to be done. Conversion of dopamine into norepinephrine. So with the wall of this membrane, there is a very special enzyme here, right? Now, this enzyme is attached in the internal wall of the internal side of the vesicular membrane, right? What this enzyme is doing? Who is going to tell me? It is going to do work on the dopamine, one more action. What is that action? Dopamine beta hydroxylation. There will be one more hydroxylation done by this, right? By this enzyme. And this point, this is a beta carbon. So at this carbon, it will add what? Hydroxylation. And when this point gets hydroxylation, now the compound is called, yes please, this compound is called norepinephrine. So what really happens, that dopamine is acted upon by this drug, by this enzyme. The name of the enzyme is dopamine beta hydroxylase. In some book, they call it dopamine beta oxidase. It's same thing. But anyway, majority of the authors, they write it dopamine beta hydroxylase. So those neurons which release norepinephrine, in their vesicle, this enzyme is present. But those neurons which release dopamine, they don't have this enzyme. Am I right? Claro? Now, we have converted dopamine into, yes please, norepinephrine. In this way, these vesicles keep on concentrating the dopamine and converting into norepinephrine, and norepinephrine molecules keep on accumulating. Then what will happen? What will happen if norepinephrine molecule keep on accumulating? The osmotic power, osmotic pressure in the vesicle will become very high. It may automatically burst, and we don't want that. So this norepinephrine is complexed with some proteins inside called chromogranin, or with ATP and some ascorbic acid. So what happens? This norepinephrine is complexed with some internal proteins and ATP. So norepinephrine molecules will be binding with them. And you know, osmotic pressure is directly proportional to the number of molecules, not to the size of the molecule. So when they are kept together like a group, osmotically they act not as 1, 2, 3, 4, 5. They don't act as 6 molecules osmotically. As a group they act as 1 molecule. Am I